Hey folks, this is the last video that I'm recording for our kinetics section. So in this video, I'm going to be talking about reaction mechanisms. So this is really the first time in your chemical education that you're learning about reaction mechanisms. For those of you that go on to do chemistry, those of you that are chemistry majors, you'll talk about mechanisms in nearly all of your classes. And so it's hard. Reaction mechanisms are really challenging. You have to have what I like to refer as chemical intuition to be good at these. So this is really just an introduction, right? This is not like mastery of reaction mechanisms, just an introduction, okay? And so a reaction mechanism is the set of steps that describe how a reaction occurs at a molecular level. So, and we've had some hint of this or some notion of this in your general chemistry classes, that chemistry doesn't occur in one step, right? There's often multiple steps. And those multiple steps are called elementary steps, okay? Which is the molecular view of a single process taking place in a chemical reaction. And within those elementary steps, we can create what's called intermediates. So an intermediate is a species that's produced in one step of reaction and consumed in a second step. So an example of this would be if I have a simple two-step mechanism in which a reactant first reacts to form an intermediate. So reactant becomes intermediate, and that intermediate is short-lived and unstable, so that intermediate can also go on to react to form a product. So this would be an example of a very simple two-step mechanism where each of these are the elementary steps, okay? And then so the molecularity, the number of ions, atoms, or molecules involved in an elementary step. So if we know it's an elementary step, then we can actually use the stoichiometry of the reaction to get the order. So for example, if I balance this whole reaction, right, the intermediate and the intermediate cancels, and it just looks like it goes, A goes to products, okay? So this would be my total reaction, and then this is my mechanism, these two individual steps. So the mechanism has to be consistent with the overall reaction. So the mechanism has to add up to the total reaction. And also, because I know these are elementary steps, I know because there's only one of these A's, that means it's a first order. And because there's only one of these intermediates, that also means it's a first order. But I can't necessarily say that about the total reaction. I can only use the stoichiometry of individual steps to infer the reaction order. Okay, so here's kind of a summary of that, of these molecularity steps. So if we know these are elementary steps, meaning someone's told us or we're guessing, you know, these are not the global reactions, right? If I just simply have A goes to products, we call that unimolecular. It's first order because it only involves one molecule, and the rate of just this step would be rate equals K times A. So suppose I know the elementary step is A plus A, or in other words, it goes, 2A goes to products. Then that's bimolecular because it's got two A's, and then it would be second order, rate equals K times A squared. Another way we can make a bimolecular elementary step is by A plus B, right? And then it would be K times A times B. And then anything beyond two molecules, we call termolecular, meaning many molecules. So that could be 3 or 4 or 5. So for example, if our mechanism, one of our steps is A plus A makes B, or 2A makes B, then we would say it's second order in A and first order in B. So the rate of just this step would be K times A squared times B. Or if it was A plus B plus C, then it would be K times A plus B, or excuse me, K times A times B times C. But again, consider these are not the total reactions. These are just for the elementary steps. Okay. So here's an example we can look through. So the balanced equation for the reaction of gaseous nitrogen dioxide and fluorine is the following. So two NO2s react with one F2 to make two NO2F. This is the total reaction, okay? A suggested mechanism for this reaction is a two-step reaction, one in which there's a slow step, and then the next in which there's a fast step. And then the question says, what is the rate law for this reaction? Well, first of all, let's just see if this reaction mechanism is consistent with the total balanced reaction. Okay, so I'm going to write down the individual steps. And we note here that we can see right away F atom is an intermediate, right? Because it's appearing as a product, but then disappearing as a reactant. So that's going to cancel out. And then when I add these two together, I get 2NO2 plus F2 makes 2NO2F. And let's see, yes, that's consistent with my main reaction. So that's good that that's consistent. And then someone also told me that the first step was a slow step and the second step was a fast step. And I'm going to get into in a minute how we know this one would be slow and how we know it would be fast. For now, someone's just told us, okay? And so now if you think about this, if we go back to that example that I gave you, like where you're driving down to the Bay Area in your Tesla Roadster and you're going crazy fast, but then it doesn't matter how fast you can go because you get stuck behind traffic. So the fastest you can be is based off of your slowest step. So this becomes your rate determining step. The slow step is always the rate determining step. And because we can see that these are individual elementary steps, then I know that I can write directly that this step, I'll put slow here and fast here. We know we can say the rate of this step is rate times K times NO2 times F2, just based on the stoichiometry of the reactants. And then we know the rate of this step is K times NO2 times F, all right? But because they're telling me this is the slow step, the reaction only proceeds as fast as the slowest step. So this is the rate law for the total reaction. For the total reaction, that's the rate law, one NO2 and one F2. And if you looked at the way this reaction is balanced, it's got two of these and only one of these. So you might think that it should be NO2 squared, but it's not, because the mechanism only involves one NO2 and one F2 in the slowest step. Okay? So how would we know this is slow and how would we know this is fast? Well, this is what I was kind of referring to earlier about having chemical intuition. And for now, it's probably going to be very difficult for you to know which step in a mechanism is slower and which step in a mechanism is faster. So in this class, you're pretty much going to be told which is slow and which is fast. But here's how I would know that. So let's go through and kind of apply this whole chemical intuition. And the way I like to apply the chemical intuition is I'm going to start looking at these individual steps and their Lewis structures. So if I look at NO2, if you recall, NO2 is actually a radical. It's got one unpaired electron, so it looks like that. And of course, there's resonance structures associated with it, but we'll just keep only one for now. And then we know F2 looks something like this, okay? And if we can see, we've made a single F atom on that product side, and I know a single F atom only has 7 electrons around it. And if I look at that NO2F, I could start to infer that it's going to have to look like this if I did the Lewis structure and followed all the rules. And the reason why I know it's going to have to look like this is because now I can kind of start to see what needs to happen. One of these F bonds needs to break. And so if I look at this F right here, 2, 4, 6, 8 electrons, I'm going to send one of these electrons off to that F atom, okay? and that's what that arrow represents. And I'm going to send another one of the electrons in the chemical bond off to that F atom. So that's the bond breaking. And then now this single unpaired electron right here can go and hook up with this electron right there. Okay, so let's call these fishhook mechanisms that involve single electrons. And so now what I've done, if you think about this, I've got one electron from this bond and the one unpaired electron right here forming a new chemical bond that I see right here. Then this bond has been broken and I've now got this F radical. And if I look at my second step now, there's another NO2, okay? And I've got F atom, and so there you go. I've got one unpaired electron and another unpaired electron, and they combine to form a new chemical bond, and that's going to make a second NO2F. And now, so I've got both of these steps chalked up with their Lewis structures and the arrow pushing. That's what we call this, pushing electrons around. And now if I think about why this step is slow and why this step is fast, is because there's a lot of stuff going on in that slow step. So first of all, these have to get in close proximity to each other, right? They have to diffuse and find each other and collide. And then when they collide, this bond has to be broken, and then a new bond has to be formed. And that takes time. F2 is stable. It doesn't want to break apart. So it takes time for the NO2 to force the F2 to break apart through that collisional energy, okay? And then now, once we've created this unpaired electron in this F atom, this thing is the intermediate, right? It's really unstable. It's going to react really fast because it's unstable, and it's going to combine with another NO2, and that's what makes that really fast. So this is kind of how we use that chemical intuition to guess this would be the slow step, and this would be the fast step, and that's why I know the rate has got to be K times NO2 times F. So first order in F and first order in NO2, meaning the reaction rate is only dependent on, oops, let me write that better. K times NO2 times F2. And when I think about what this is really going on, the fact that it's first order in NO2, first order in F2, that's because in the rate determining step, there was only one NO2 and one F2 involved to make the whole reaction proceed. Okay? So that's what I want you to be able to recognize with these mechanisms and rate determining steps. If you know which step in the mechanism is slow, that's going to be the rate determining step. And again, I'm not going to make you come up with that. You'll likely be told one step is slower or faster. But I do want you to kind of be able to rationalize maybe why one of these steps would be slower or faster if you're told those relative rates. Okay? So now moving on. So here's another example that we could go through. All right. And so let's see. So if we consider the total reaction, 2NO2 makes 2NOs plus O2s. They're telling me the observed rate law. So they already said the observed rate law is K in O2. Here's the proposed mechanism. And I didn't say this previously, but all mechanisms are proposed. There's no way we can shrink ourselves down to the size of molecules and physically see like all these individual steps going. But there are some chemists like myself, who that's what you do in your research, is you actually try through experimentation to figure out what these mechanisms are. And it's really hard, but I think it's pretty interesting. Anyways, so in this problem, they said, they gave us the total reaction. They said the observed rate law is KNO2 squared. And so now when we're looking at these two steps, this step actually involves two NO2s. This step only involves one NO3. So this step number one has to be the slowest step because its stoichiometry is consistent with the observed rate law. Okay? And so what we would see from an activation energy point of view, so you can actually work out a mechanism from this activation energy graph. And so remember we talked about these kind of graphs last time. And so this is an endothermic reaction. starting with NO2 right here, two of them specifically, and then ending with 2NO plus O2 over here. And this is actually how we know that it's two steps, because there's two activation energies, right? So you can see that first one has the really large activation energy, which is what makes it slow. But then the second one has a really small activation energy, which is what makes it fast. And this is very typical actually in chemistry. This is not like a general rule, but this is very typical in a two-step mechanism, that the first step will typically be the slow step, because the first step is what requires some type of initiation or activation, right? And then generally the rest of the mechanism will proceed quickly. Okay, so that's a general rule that works most of the time. Okay, so moving along. So I want to talk about catalysts now. And this has its own section in the book, but I think this goes really well with what we've been talking about with mechanisms. So a catalyst is a substance that speeds up a reaction without itself being consumed. And so we'll talk about how that works in the mechanism, how a catalyst can speed up a reaction, but it's not consumed. And so we just talked about intermediates. An intermediate is a substance that's formed from reactants and goes on to react further to form products. So for example, we know that an intermediate mechanism looks something like this. A reactant A goes to an intermediate, and then the intermediate becomes a product. And so overall, that looks like A goes to products. Okay? But now in a catalyst, it's very different. So in a catalyst, something is usually consumed as a reactant, but then regenerated as a product. So for example, we might see something like A plus B goes on to form an intermediate, okay? So then that B is getting consumed, but then that intermediate could go back out and make B again, and then finally that A could go on to form products. I'm not making a very good mechanism here, sorry about that. But in any event, in this case, B would be our catalyst, whereas I is our intermediate. So they appear in opposite places in the mechanism. And I'll do a real example of that, a better example. Okay. And then now as far as what the activation energy looks like, so if you look at this graph here, you can see the uncatalyzed reaction mechanism would have a much larger activation energy than the catalyzed mechanism. So that's why the catalyst speeds up the reaction, because it lowers that activation energy. Okay, so here's a very famous example, catalysts and the ozone layer. So this is like a quick 2-minute lesson on environmental chemistry. So if here is ground level where we live and breathe and eat and stuff, and like, you know, here's maybe a tree, and here's like a car. This is like a, wow, really bad looking car. Here we go, wheels and something like that. Okay, right there's a car, and it's spitting out automobile exhaust. And then way up here is the O3 layer, the ozone layer. And that goes like, you know, 35,000 feet and up, like where airplanes fly, okay? Not where we breathe. So we want this ozone layer because it filters out harmful UV radiation, but allows visible radiation to pass through. So that's a good thing. So we'd have a lot of harmful UV radiation if it wasn't for the ozone layer. But this would be, so this is what I call the paradox, that ozone is also toxic to humans and plants and animals. So pollution can actually generate O3 down at the ground level where we live, and that goes on to create smog. And I'm going to talk about this in a moment. So these are two different environmental problems: the creation of smog and air pollution, and the reduction of the ozone layer. So it's a paradox in that we need ozone way up here to live, because with all that harmful UV radiation coming down, that would be carcinogenic, that would give us cancer. Um, However, but we can't breathe it in because it's toxic. So if we had ozone down here where we live, ground level, it would poison us. So it's a paradox, right? We need it way up here to live, but if we have it way down here, it'll poison us. So if we now talk about ozone layer depletion, so what was going on in the 50s, 60s, and 70s, we had introduced these compounds called chlorofluorocarbons, okay? And as it turns out, those destroy ozone. So here's the mechanism for O3 decomposition, which occurs naturally. And so that ozone layer will absorb that sunlight as I just showed you, and it breaks apart into a single oxygen atom. So that single oxygen atom, that's our intermediate, right? And releases an O2, and the overall net global reaction is 2 O3s become 3 O2s. Now, ozone is also regenerated naturally in the atmosphere. It goes through seasonal cycles, okay? So what ended up happening, though, we started using these chlorofluorocarbons as coolants. They work really well as coolants. So you hear like incorrectly that it's aerosols that destroy ozone. That's not correct. It's chlorofluorocarbons specifically. You can have aerosols which contain chlorofluorocarbons, but if you have an aerosol that does not contain chlorofluorocarbons, it's not going to destroy ozone. So in any event, what ends up happening is these CFCs is what they're called, chlorofluorocarbons. They don't react with anything. So these CFCs percolate all the way up to the upper atmosphere. And then once they cross above the ozone layer, they react with that ultraviolet sunlight and release a chlorine atom. Okay? And so now there becomes a new mechanism here. That chlorine atom, right? Remember, we talked about that with fluorine. Chlorine, right? It's a single radical. Radicals are really, really reactive. It wants to react with that ozone. And it's quite efficient at reacting with that ozone. And you notice here in the mechanism, Cl reacts with O3 and makes hypochlorite, ClO, and O2. But then the ClO reacts with O3, regenerating chlorine and O2. Right, so if I write that down here, Cl plus O3 makes ClO plus O2, and then ClO plus O3 regenerates chlorine plus O2. And so the overall reaction of this is 2 O3s become 3 O2s. It's the same reaction that I showed you up here for the natural decomposition. However, this catalyzed decomposition occurs really fast, much, much faster than the natural process. And if you notice here, we've got two things going on. We've got the hypochlorite intermediate, okay, because it appears as a product and then disappears as a reactant. But then look, the chlorine gets consumed in this reaction, but then regenerated in this reaction. So that makes it a catalyst because it's getting regenerated. And actually, there's been a lot of folks have studied this mechanism. So this won the Nobel Prize in the 90s from Sherry Rowland, who was a professor at UC Irvine. That's where I went to grad school to study atmospheric chemistry, and I got to meet him. Really, really cool, really influential guy, really, really impressive scientist. So he took on the chemical industry. Dow Chemical Company are the ones who created this, and it actually created a worldwide movement to ban chlorofluorocarbons. And because what people had discovered, as it turns out, if you have one Cl radical catalyst, it'll destroy 10,000 O3 molecules. So for every one single chlorine radical you put in the upper atmosphere, it destroys 10,000 ozone molecules. So that's way out of whack for that natural depletion and creation. And so back to this graph that I have up here. So you notice now So what started happening was they started accumulating in the southern hemisphere, and I don't want to get into those reasons why, but you should certainly read more about this if this is interesting to you. But what you can see, what started happening in the 80s and the 90s, this hole started getting bigger. It started getting bigger and bigger and bigger. And then we did something in 1995. Many of you weren't even born yet. That was called the Montreal Protocol. It was a big sweeping set of environmental legislation. And you can kind of think of that similar to like the Paris Accords that were just a few years ago, or the Kyoto Protocol that was about 10 years ago. So this was the Montreal Protocol. So all of the world's nations got together in Montreal, and they decided in 1995 we're no longer going to use chlorofluorocarbons. We're going to ban them worldwide. And what started happening, it's kind of hard to see, and this graph only goes out to 2010. There's like 10 more years of data here, but now the hole is starting to shrink again. It's starting to recover, which is really cool. So it's kind of the evidence that environmental legislation really works. And particularly, it was scientists who discovered this and pushed this through Congress and the Senate, and they actually got laws passed to ban these chlorofluorocarbons, and it's making a difference in the world. So there's another story that I want to tell you with environmental chemistry and kinetics, and that's related to this that I pointed out earlier, this smog formation. Okay, so automobiles emit, so when we combust, let's say, all right, hydrocarbon. So hydrocarbon, right, like gasoline, okay, reacts with oxygen and makes CO2 and H2O. And I think you've been told, and we've talked about this ad nauseum, CO2 is a greenhouse gas, right? It's warming up the planet. But what can also happen from this, so this is the total reaction of combustion. In the mechanism of combustion, there are small molecules released called VOC, volatile organic compounds, as well as NO, as well as NO2. These make up what we call NOx, and this is why you actually get your car smog checked, because as it turns out, let me write this again. This is a fun mechanism. So NO2 reacts with sunlight to make an oxygen and an NO. So that's why NO2 and NO are often viewed with each other. Okay? Let me start from the beginning. Excuse me. I'll start from the very beginning. Nitrogen and oxygen react under really high heat to make two NOs. Okay? So that's the first step that happens. So this actually happens in your tailpipe, or it can happen in large industrial processes. This would not happen at low temperature. Nitrogen and oxygen do not react at low temperature. Only at high temperature does this become important. Okay? So then what you get is NO can react with O2 to make NO2. I'm not doing a very good job showing the final balanced reactions. But then NO2 can react with sunlight to release an oxygen atom and another NO. So you can see NO functions as a catalyst in this case. But then when you go to make that oxygen atom will react with O2 to make O3, and then O3 reacts with volatile organic compounds to make smog. So this is the mechanism of smog creation in urban atmospheres. And this is specifically what I study in my research. This is exactly the type of chemistry that I do in my lab. If you look at, this is a typical profile of atmospheric chemical concentrations, starting from 4 in the morning all the way to 4 in the afternoon. And what you notice at 4 in the morning, NO, NO2, O3, and volatile organic compounds, they're all very low in concentration. And you notice something happens at about 6, 7 a.m. Rush hour, right? People get in their cars, they start driving. That initially is what creates NO through this first step. So NO starts to build up. And as NO builds up to some critical level, and then as the sun starts to come up, right, that starts to make NO2. And NO2 starts to build, but as the sun continues to rise, right, to higher and higher latitudes, to higher angles, higher zenith angles, the NO2 will also peak and then start to get destroyed. And then as that happens, it starts creating O3. And then you notice now, by the time it's about noon or 2 o'clock, the VOCs are starting to go down because they're reacting with the ozone, and that's creating this smog. And all of this, as the sun starts to go down, and there's another wave of this with the second rush hour happening at 5 o'clock, but sunlight is what's driving all of this. That's why we also often call this photochemical smog. It's driven by automobile exhaust and sunlight. And so this, eventually when the sun goes down, all of these decay. We're back to actually having fairly clean atmosphere. But then when the sun comes back up again, the smog cycle starts all over again. And so you can see these pictures of like Hong Kong and Los Angeles. Those of you that are from LA or even the Bay Area, you're used to what smog looks like. Interestingly, what's going on right now, this is historically unprecedented. The air quality in LA right now, as a result of everybody doing the shelter in and staying home, it's at all-time record lows because we're not having any of this automobile exhaust. And so it's really, really good evidence that if we stopped consuming fossil fuels, if we switched our automobiles over to electric, like not even hybrid, because hybrids still burn gas. The hybrids cars can still make smog, as it turns out. Ethanol, biofuels, all of those, they still make smog. In my opinion, the best way to really curtail air pollution is if everybody had an electric car. And that's what we're seeing right now. You're seeing air pollution at an all-time low, which is really cool. So here's some more evidence of that. So first, let me talk about the catalytic converter. So the catalytic converter, this is something that all of you in the state of California should be aware of. Don't blow off getting your car smog checked. I'm a big stickler about this. Smog checking your car is what keeps the buildup of NO and NO2. And if you think about this smog mechanism, it all starts with NO and NO2. So if you can limit NO and NO2, then you can limit smog. And so what the catalytic converter does here, what you notice is it allows these NO molecules that are getting created from this internal combustion engine from N2 and O2 reacting under high heat. Remember, this takes place in your engine where there's lots of heat. Okay? So you've got this palladium catalyst, and the way this palladium catalyst works, I'll just kind of draw it as a cycle. Okay, the NOs land on the palladium, as you can see right there, and platinum catalyst, PT. And so when they land on that platinum catalyst, the platinum donates electrons to the NO. So this is a redox reaction. So the platinum, because it's giving away electrons, it is being oxidized, so it's functioning as a reducing agent, all right? And then now this rearrangement happens where now instead of having NO, look, the nitrogens and nitrogens and oxygens are aligned. And when this happens, the electrons are given back to the platinum, and then nitrogen and oxygen get put out in the exhaust. Okay, so you can see this is why the platinum is the catalyst. It's the catalytic converter because it's always going round and round from its +2 state back to its 0 state. Okay, and what this does is greatly reduces the amount of NO. And I'll show you the evidence of how this works. So these are historic ozone air quality trends in Greater Los Angeles. This is all data that I downloaded from the internet. I haven't updated this graph since about 2015, so I'm about 5 years behind now. But what I want to describe to you, there's several things going on. So let me just walk you through this graph. So On the x-axis is time, starting in 1975 up to 2015. And on this red y-axis, that's the number of stage 1 smog alerts. Many of you will not know what that is, but if you're from the LA area, if your parents were in LA in the 70s, you should ask them what a stage 1 smog alert was. So that was equivalent to the same type of air pollution we experience during forest fires, when everybody has to stay inside and wear masks and it's toxic to be outside. That's a stage 1 smog alert. They tell children and elderly to stay inside because it is literally toxic for your health. And if you look at this, 1975 or 1977 or whatever, there was 120 stage 1 smog alert days for that year. There's only 365 days in the year. And this was not like due to forest fires. This was just the regular weather conditions, the regular air pollution conditions in the greater Los Angeles area. Every third day, you had to go inside. And then on the blue scale right here is the maximum 8-hour ozone concentration. So again, because ozone leads to smog, we can use ozone as a means of tracking smog. Okay? So if there's high ozone concentrations, there's a lot of smog in the air. Excuse me. So you can also see in the 70s, on these days when there was a lot of stage 1 smog alerts, ozone concentration was high. So then what happened in the 70s? The EPA was created. In 1975, the Environmental Protection Agency was created. They created the Clean Air Act, which established the rules for catalytic converters in the state of California. It also established, this is really important if you've paid attention to the battle between the Trump administration and the California Air Resources Board. The original Environmental Protection Agency and the Clean Air Act in the 70s established that states can make their own environmental regulation. So California can have stricter environmental regulation than, let's say, Indiana, because California is having a lot more issues based on the local meteorology, based on the fact that you've got, like, here this ocean, right, and there's Long Beach, and then this mountain range right here. And so when the wind comes in off of the west coast, it gets trapped in this mountain range, right? This is like the Inland Empire right here. This is LA. So there's a really unique set of geological and meteorological conditions that make LA so smoggy. It's not only because of the cars, but it's because of our local meteorology and geology. So in any event, in the 70s, Clean Air Act is established. It allows California to set its own regulations. California says everybody has to get smog checked. And it also established that as new automobiles come out, when new automobiles come out, if they're to be sold in the state of California, they have to meet certain stringent emissions requirements. And look at the results. The results are the number of stage 1 smog alerts are decreasing, and the ozone maximum average concentration is decreasing. And what I want to point out, there's something really amazing going on. There was a local spike right there in the 90s, and I think that local spike was actually due to forest fire. And every now and again, we will see these local blips where we have historically bad forest fires. Those lead to these smog alerts, okay? But you notice there's been like 20 solid years here without a whole lot of stage 1 smog alerts. And what I want to point out is in 1998, there was 4.8 million registered automobiles in LA County. That's not trucks, that's not motorcycles, boats, that's just personal automobiles. 4.8 million in LA County alone. In 2014, there was 6.3 million registered automobiles. So look at this. There's been an increase in like what? Almost 2 million, 1.5 million new cars on the road without creating any new pollution. And this is because California is leading the world in environmental regulation. California requires our gasoline to be cleaner than anywhere else. It requires our catalytic converters to function better than anywhere else. It requires you people to go get your car smog checked. which you definitely should do. Don't blow that off, please. It's our air that suffers if you don't get your car smog checked. And then what's been happening with the Trump administration is they're trying to sue the state of California for setting their own emissions. When the state of California says, hey, no, we're legally allowed to set our own emissions. And besides, why would we want the same emissions as a state like Indiana or New York or whatever that have a different set of meteorological and geological conditions? So in any event, that was a long-winded story. I could give like whole hours upon lectures of environmental chemistry. But in any event, this is what I do in my own research related to kinetics and environmental science. And I'm also very passionate about environmental legislation, if you can't tell. So anyways, I hope you enjoyed this. I hope you learned something about kinetics as well as environmental atmospheric chemistry. If you're interested in this kind of chemistry, atmospheric chemistry, you should come talk to me because I'm always looking for new research students. You know, assuming one day when I can get back into my lab again and start doing more research. And also, you should read about what's going on right now with these unprecedented lows in air pollution. It's pretty amazing. It tells a really nice story and it makes a really good case why we should all be eventually going to electric cars. Not hybrids, not biofuel, no fossil fuels whatsoever. We're going to see more of this rapid declines in air pollution if we can completely rid ourselves of fossil fuel dependency. All right, folks, that's it for kinetics. We'll start electrochemistry next. Hasta luego.